need. That's a camera here. Actually, I try to use that thing. Documents. Can I use the document camera? Or is that?
No, document camera will be much more quality.
I have to show that here. I don't know if that is good. I think if I do the document because I have CD on there. Somebody else coming out, so basically.
I'll check if she is available.
He's a physical chemist, so follow the talk, I guess. You're a physical chemist, at least.
Yeah,
So you understand what he is talking about.
we'll find out. I didn't read the abstract, so I don't know what you're going to be talking about. Even though it looks like you had graphene on your intro side.
So that's the bio you emailed. There were not too many dates on it, but
I did email that.
that was on a copy on the abstract also.
Let's do this out. No, take it.
So that's it, I guess.
Yeah, it can be.
Let's have a look. So German fellow again. So I kind of the habit to invite Germans, I guess. So it was kind of unusual that you went to Newcastle already after your diploma. It's a little bit unusual. I don't know what was the motivation. Just an opportunity.
Just go somewhere else.
Because most people leave after their PhD, do a postdoc, right? Leaving before the PhD is relatively unusual, but it was fairly good. And we met actually in LA, both postdocs at that time. That must be almost 20 years ago or something.
Almost. Not almost.
So we have a history of going on strange trips together. That reminds me to the weather here. So I don't know if you still remember that. We went on a trip to Las Vegas.
Yes.
And what we did not know is that was the Father's Day weekend or something. So it was totally booked out. We did end up pretty far from the strip in some kind of Holiday Inn thing. So I don't know if you remember that, driving through Death Valley to Las Vegas. That was, I think, when we were in Gail's group at that time. Then I did another postdoc regarding Zurika, became a faculty member. So I have lots of grants, so very successful. Lots of publications, lots of physical reference letters, publications. Career grants, so lots of invited talks. So I have only 10 or so invited talks, so it's a lot of invited talks.
Thank you for another invited talk.
So let me switch back to the what button do I need to push it? The laptop or something? Computer, laptop button? Laptop, I guess.
All right. Okay, I guess thanks for the introduction. It's certainly a memorable invited talk. Said I'm at the University of South Florida, and at least you can't blame me for the weather. I did bring it with me. So I'm going to talk about 2D materials, broadly more specifically on transition metal dichalcogenides. The work I show was done by students in my group. Horacio was very instrumental in it, Maggie, Paula, and Kinga, the ones who carried it on. So some synchrotron data from harvest measurements, which which were done in Paris at the Soleil Synchrotron, together with Maria Asensio and Jose Avila. I have one slide on actually chemistry related, which was done by actually Stefano Agnoli in Padua in Italy to do electrochemistry on some of the defects we synthesize. And we have theory collaborators mainly doing DFT, which is Arkady and Hanu, one in Germany, another one in Finland. And actually, I have Carmelo on here, but actually I'm not going to show anything that's more sophisticated one-dimensional electron systems, which I took out of this presentation. Okay, you may wonder about the title, A Journey Through Flatlands, and I'm not sure how versed you are in literature. There's a kind of famous...
I use the same thing for one of my talks actually.
Ah, there we go. Everyone uses that who talks about 2D materials. Flatland, this is a novel from Victorian Britain, where the author, Edwin Abbott, uses the analogy of dimensions to relate the disconnect within the society. So it's a romance in many dimensions, and that's what I wanted to stress. It's not just two-dimensional materials I'm going to talk about, but also one-dimensional. So the main character in this novel is a square, obviously a two-dimensional character, and here he goes to the one-dimensional world. Here's a line, and he finds it very difficult to connect with them because they only can see him as a one-dimensional object and doesn't see him in his, what he has to offer in total in the two-dimensional space.
Did you read something actually?
No. And I write the summary. That's some part of it. So there's also a movie or an animated movie idea for Flatland, which I may watch one day. But anyway, so my Flatland is 2D materials, and there's a whole set of two-dimensional materials. Probably the best known one is graphene, two-dimensional honeycomb structure of carbon. But there are a whole range of other materials that have many different properties. Obviously, graphene is a semi-metal. We also have insulating materials. Best insulating is hexagonal boron nitride, which is the same structure as graphene, just exchanging carbon with boron and nitrogen. And then there's a whole range of interesting semiconducting materials that have potential maybe for applications. Materials class I want to talk about is transition metal dichalcogenides, which are essentially three-layer materials where you have a metal layer sandwiched between two layers of chalcogens. So either sulfur, selenium, or tellurium. And what's interesting about that family is that it spans a wide range of properties. The most famous or most recognized ones are the semiconducting ones, like molybdenum sulfide. But there are also metallic ones. So I'm doing work on vanadium selenide and titanium selenide, which are metallic, and even superconducting ones like niobium selenide and so on. And so especially the metallic ones have a lot of interesting many-body physics problems like superconductivity or charge-density wave behavior. Now, the nice thing about 2D materials are obviously that they only have strong covalent bonding in a plane and are weakly bound out of plane, and that allows you to isolate them as a single atomic or molecular layer, and then it's an obvious idea to reuse these single layers and restack them and make completely new materials by combining materials, different two-dimensional materials on top of each other. And Andre Geim, who was one of the Nobel laureates for work on graphene, came up with this picture, and he suggested that it's similar like playing Legos, just I guess Lego grown-ups. They can take different Lego blocks and stack them on top of each other. But there's obviously a disconnect between macroscopic Lego blocks and atomic scale, nanoscale graphene sheets. And so I will talk something about why these are not just Lego blocks. Well, transition metal dichalcogenides, as I said, are these tri-layer structures with metal atoms and then sandwiched between chalcogen atoms. And then in the bulk material, like here for molybdenum disulfide, they form a three-dimensional structure where you have this van der Waals gap between the sheets, and then that is the 3D material. You can use those crystals. Molysulfide is something you dig out of the ground. It's a mineral you can find, or you use it in your car engine as a lubricant. So you can take that bulk crystal and exfoliate it with the famous Scotch tape method. Just peel off layers, and if you peel it often enough, then you may end up with a single layer and then characterize those. In my research, I want to grow them directly, and the method for growth I'm using is molecular beam epitaxy, where you have different sources with different components. So for example, for molysulfide, you would use a molybdenum source that evaporates molybdenum, and a sulfur source. Also, my work, I'm mainly growing selenites, so you would use a selenium source. And so both ways essentially allow you to grow single layers of these materials and study their properties. One question would be, how are single layers different from bulk materials, or are they just the same properties of bulk materials, since they only interact via weak van der Waals interactions? Right. So just a word about the growth. As I said, I grow with van der Waals, with molecular beam epitaxy. Of course, you need the substrate to grow on. In my case, I mostly use other van der Waals materials as a substrate. So, for example, bulk molybdenum disulfide would be a good substrate, or just graphite would be a substrate to grow on. And then we characterize it with scanning tunneling microscopy. And what you see here, I think this is vanadium selenide, is this island growth. So every island here is a single layer of vanadium diselenide, and then in between you have the substrate material. In this case, I believe it's molybdenum sulfide. And then you can characterize the properties of these monolayers. These are with scanning tunneling microscopy, so you can zoom in and look at the atomic structure. So this is the atomic corrugation of vanadium selenide. But the one important point I want to make is, although you grow on a van der Waals substrate, the grown films is rotationally aligned with the substrate. And the best way to see that is from electron diffraction, where here now you have two van der Waals materials on top of each other. So you get two sets of diffraction spots, one from the substrate and one from the film. It's hard to resolve here, but here you see two little spots. One, the outer one, is from the molysulfide substrate, the substrate with the smaller lattice constant. And then you have another spot here, which is vanadium selenide, which has a smaller lattice constant, so it's more to the center of the reciprocal space. But the important part is that the spots are aligned in the same rotational direction, which means that the film we grow is in the same orientation as the substrate, and that's what we call van der Waals epitaxy. So also the film and the substrate have independent lattice constants, so they're not stretched, they are rotationally aligned. All right. So what I want to talk about here today is the first part is diving into why monolayers of van der Waals materials are not just Lego blocks. And then in the second part, I'm going in my romance of many dimensions from the two-dimensional space to the one-dimensional, and talk about line defects in 2D materials. So why a single layer is different from bulk materials? And I guess the nicest example is this paper, which is already almost 10 years old, where they looked at molybdenum disulfide and exfoliated it with a scotch tape method. And so you get little flakes, and this is a flake of moly sulfide, and the holes, it's put on a TM grid, so the holes are just holes in the transmission electron microscopy grid, and this is the flake. So there's just an optical microscope. You can see a darker region, which is bilayer, and a less dark region, which is monolayer of the same flake. Now what's interesting is if you don't look in optical microscopy but in photoluminescence, so you look at the light that comes off the material after you shine light off, then the bilayer you cannot see at all. There's no light coming off. While the monolayer is photoluminescence. And that kind of photoluminescence is an indication for a direct bandgap material, because here you can have obviously a direct click combination of an electron and a hole, and that gives you strong photoluminescence. While if you have an indirect bandgap material, or recombining an electron and a hole, you need to change the momentum, so a phonon would be involved in that process, and that makes it a far less efficient process. And so the bilayer or multilayer material seems to be an indirect bandgap material. So what that simple experiment shows you is that you have, as I say, a new direct gap semiconductor, which is a monolayer material of moly sulfide. And we do understand that fairly well. And there have been many calculations. This is just an example. So if you look at the band structure of molybdenum sulfide, it's indeed an indirect bandgap material. But if you go to the monolayer, then it becomes a direct bandgap material. And the biggest change here is really at the gamma point, where the bulk material has its maximum. And then for the monolayer material, this valence band is reduced in the binding energy. It's a lower binding energy, which makes a shift, or shifts the valence band maximum from the gamma point to the K point, and it becomes a direct bandgap material. Now, why is that? Why is there this change in the binding energy at the gamma point? And that comes from the molecular orbital character of the bands at the different points in the band structure. So if you see here, it's a K point. Here, essentially all the molecular orbitals are located at the molybdenum plane and are in plane of the molybdenum plane. So if you stack those on top of each other, this molecular orbitals doesn't see anything of the next layer of the molecular orbitals of the next layer, and those orbitals do not interact at all. While at the gamma point, which is up here, you have these orbitals, the molybdenum Z orbitals that stick out of the plane. And so if you have another plane on top, then these orbitals can interact with each other and partially overlap, which gives a rise to their energy, binding energy are going to be higher, and that makes the gamma point to be the valence band maximum because of the overlap of orbitals. So the change from indirect to direct bandgap material is really a consequence of the interaction of the molecular orbitals in the planes, where only part of the band structure interacts strongly or interacts between the different layers, while other part of the band structure does not. Now, so this is a very nice example why monolayer materials can have very different properties than bulk materials in the electronic structure. Now, we ask, can there also be structural variations due to interlayer interactions? And so we were interested in this material, vanadium ditelluride, which in the bulk doesn't have a simple structure as the molybdenum disulfide, for example, but has this additional structural distortion in the unit cell. So every third cell of tellurium atoms are squashed together, and then they stack on top of each other, making this monoclinic unit cell. And the question is this distortion of the vanadium ditelluride structure a consequence of interlayer interactions? One reason why we might think that it's just from a naive picture that if you look at the distortion, it looks like a gear wheel structure where these are the teeth that go into the hole of the other layer, so that allows them to stack differently. So to study that, again, we have to grow this material first. So we grow vanadium ditelluride, different layers, so that this is a monolayer structure. I think this is grown on graphite, so this line that goes through here is just a step on the graphite substrate, and then you have monolayer islands of kind of merged together of monotelluride. If you grow the bilayers, and for some reason the step edges become much better pronounced. So you have a bilayer structure on top of a monolayer, and then you can grow thicker films, and you can see the film starts to roughen, so you get many layers exposed, and you get these different terraces. But the main point is that we can grow from monolayer to multilayer fairly well defined molybditelluride. Now, if you look at bilayer or multilayer structure, we get this corrugated structure as we expect for the bulk structure, and because of this corrugation, you have not a simple hexagonal structure, as you can see, but has this superperiodicity, which is a 2 times 1 periodicity of a hexagonal structure, which we also can see in the lead, where every one of these colored structures is 2 by 1, and then you have 3 equivalent domains, so you get all these spots in your lead pattern. Now, the question is, are these interlayer interactions responsible for this distortion of the structure? And the simplest way to answer that is to grow the monolayer and look at the structure of the monolayer, where you don't have any interlayer interaction by definition. So if you do that, then behold, you really get just a simple structure. As then you get a nice hexagonal pattern, and you see also that in low energy electron diffraction, where you again have the substrate spots here on molysulfide, and then you have the really sharp vanadium ditelluride spots. So you get a structural transition in vanadium ditelluride as you reduce the thickness to a single molecular layer, and we believe that is due to interlayer interaction between the tellurium atoms. Our theorist collaborators still work on that to work it out, but we have a slight experimental evidence for that. If you look at X-ray photoemission spectroscopy, so the green line is for the monolayer, you can measure the binding energy of the tellurium core level, and then for bilayer and multilayers, this core level shifts quite significantly by 0.4 electron volts over to higher binding energies, which suggests some charge transfer from the tellurium to the vanadium, and indicates that the tellurium atoms at the interlayer interact with each other to change the valency in the multilayer compared to the monolayer. Right. Okay, so what I tried to show so far is that the monolayer has different properties from bulk materials. Then if you go to the next step, then the question, of course, arises if you make heterostructures, if you combine different monolayers together, what are the properties going to be of such heterostructures? So if you combine one transition metal dicarbonate to another. And we expect that there are new properties due to interlayer hybridization, like let's say the tellurium-tellurium hybridization of the molecular orbitals. Certainly you may get interface charge transfer from one layer to another, and then there could be other proximity effects that affect the properties, like dielectric environment of one material in the presence of the other. Another point we should make is because there's a van der Waals gap, if you grow one material on top of another, as we've seen before from the lead, there's no lattice matching between the two materials. They are interact very weakly, and therefore every layer more or less maintains its lattice constant. But if you do put two hexagonal layers on top of each other with different lattice constant, let's say here molybdentelluride on a molysulfide substrate, then they cannot match everywhere, and you get this moire superstructure. If you look a little more carefully, then you get different stackings in different portions of the moire structure. So here's a stigmoggle is the top layer, and then the circles are the bottom layer. So in some parts, you have the top layer just matching perfectly the substrate layer, but in other parts, they have more stacking as they would have in the bulk material, where one is on top of the other and the other one is a hollow side. Now, in the case of molysulfide, we argued that you get a transition from indirect to direct bandgap material because of the interaction of the out-of-plane orbitals. Now, the out-of-plane orbitals, of course, are fairly localized, and different orbitals from different layers will interact differently with each other depending if the atoms are just on top of each other or in a different stacking. And people have done the calculations for these different configurations. And indeed, what they see again is a strong change at the gamma point. It's the case for molysulfide and molysolenide, where in one case where you have the bulk stacking, again the gamma point is shifted up, while in this stacking the gamma point is shifted down. So now what you have then, if this calculation is correct, is that you have a variation of the electronic structure on this nanometer scale, as these are just a few nanometers apart, and you get a very modified electronic structure, or if you want localized kind of quantum dot structures in just the moire structure, or if you put two semiconductors on top of each other. We can do that here, molybdentelluride on molysulfide, and do STM, and you really see this strong modulation if you set your bias voltage correctly, which suggests more than just a topographic variation. It's really electronic in origin, and you can do scanning. Oops, sorry. You can do scanning tunneling spectroscopy at different spots inside and outside, and you see the variation of the band gap in these spots, which is due to the interlayer interaction between the two materials and the spatial variation of the coordination of the atoms on the top and bottom, the top and bottom layer in this case. All right. All right. Now, to summarize this part, the question is what makes van der Waals materials exciting, and what makes them different is that, first of all, the reduced dimensions make them very sensitive to the environment. So if you have a single layer, you can modify their properties much more easily than you can modify a vast material, and therefore you can tune their properties. Especially if you have van der Waals materials in a heterostructure, the adjacent layers influence their electronic properties the same way as in the bulk materials, the interlayer interaction modifies the properties. So does heterostructure modifies the properties. But in the case of heterostructure, you get the additional moire modulation that modifies the properties on the local scale. So it's certainly not the case that you can just stack the different materials on top of each other and expect every sheet to maintain the properties of the sheet, but they are changing their properties depending on how you stack them and by interlayer interactions. So second part, I want to talk about one-dimensional defects, if you want, in two-dimensional materials. So one thing which may not be recognized widely, or maybe it's too obvious, is that if you have a two-dimensional sheet and you induce an edge or a grain boundary, since those defects become really one-dimensional materials. And if you have a truly one-dimensional material, it has very different physical properties than from two-dimensional materials. If you have electrons confined in a one-dimensional metal, then you would expect very different properties like Tomonaga lattice liquid behavior and strongly correlated effects that you don't have in 2 dimensions or 3 dimensions. Right. So anyway, old famous example is molybdenum disulfide. Here from the base bubble group grown on gold. And so if you have these little islands, so this atomic corrugation of molysulfide, what they recognize is that the edges of the molysulfide islands become metallic. The molysulfide is a semiconductor, and you have the edges as metallic. They propose that this contributes a lot to the chemical properties, chemical reactivity of molysulfide, for example, hydrodesulfurization reactions. Another example here is for grain boundary in graphene, which we published already 10 years ago. So you can have graphene sheets. If you take a graphene sheet, cut it apart in your mind and translate it by a fractional unit cell and try to stitch it back together, what you get is this new configuration of carbon atoms in the grain boundary, which contains its 5-fold carbon rings and 8-fold carbon rings in a periodic manner, and so it could be does have very interesting electronic properties. The problem with graphene so was that graphene really likes a hexagonal structure so much that it's very hard to form those in a controlled or abundant way on the surface. So we really never been able to characterize it very, very clearly. Luckily, if you go to transition metal dicalcogenides, we found another grain boundary that is much more easily formed in some transition metal dicalcogenide, which is this twin grain boundary. So if you look carefully, the lattice on the left and the lattice on the right are just mirrored relative to each other, and then in between you have a grain boundary, if you want to call it a mirror twin grain boundary. And we found that those form very readily if we grow, for example, molybdenum diselenide with molecular beam epitaxy. So the same growth as before, just by co-deposition of molybdenum and selenium on the surface. You get this very dense network of these grain boundaries. And if you zoom in with the SDM, you can see that every grain boundary is this double row of bright atoms. And so the model is that you get this kind of pinwheel structure, where the pin and wheel is just alternating grain boundaries. You have one twin like that, the opposite twin, and again, and going back and forth. You get these twins, and in between you get all these twin grain boundaries. And what we image in STM are actually the selenium atoms that are neighboring the actual grain boundaries, which is shown here in more detail. So these are just the atomic corrugation of the selenium atoms. And that agrees well with simulated STM images of this structure. Right. Now, clearly they appear bright in STM. And that's molyselenide is a semiconductor. In STM, you have electronic contrast. So if you have a metallic line in the semiconductor, the metallic line will appear much brighter than the semiconductor. So just the contrast in the STM image suggests that this is really a metallic line. And now the nice thing here is that, as I said before, if you grow with MBE, it grows in a van der Waals epitaxy. So that means the film is orientated relative to the substrate, and thus these grain boundaries run in 3 equivalent directions, but they're macroscopically aligned on the surface. And this allows us, for the first time really, to do angle resolved photoemission spectroscopy to find the electronic structure of a grain boundary. which is shown here. So as I said, molyselenide is a semiconductor, so this is a Fermi level. These are the bands of molyselenide. So you have a band gap. And if you look carefully in the band gap, you get this state, which is a kind of a parabolic dispersive defect state or band gap state, which arises from these twin grain boundaries. And it seems like they intersect the Fermi level, so then that would suggest this is a one-dimensional metal embedded in a semiconducting matrix. We can look a little bit more carefully at the band dispersion. If it's really one-dimensional, what we should see is you have the dispersion along the grain boundary in the kx direction, which would be a parabola, but then perpendicular to the grain boundaries, there's no periodicity, which means in reciprocal space essentially that you have infinitesimal small separation, which gives you essentially a lot of grain boundaries, and your Fermi surface just becomes two parallel sheets of the grain boundary. So your Fermi surface should be two parallel lines. Now in STM we see we have three equivalent directions, so every direction should contribute a Fermi surface of two parallel lines. So you get three parallel lines. You can measure the Fermi surface with angular resolved photoemission spectroscopy, and indeed you get this cross-hatching of the Fermi surface, which main point is that you have parallel lines, which indicates it's really a one-dimensional property of these grain boundaries, which you can see here better. So here you have the binding energy, kx direction along the grain boundaries, and then ky parallel direction perpendicular to the grain boundaries, and you get these parallel Fermi sheets, indicating it's one-dimensional. Now I'm not sure you have any solid-state physics course, but if you do solid-state physics, one nice example is the stability of a one-dimensional atomic chain, or so-called piles instabilities that you would expect if you have a one-dimensional chain. So if you have a simple parabolic dispersion, because then at the Brionson boundary, you open a gap due to the interaction of the electrons with the periodic potential of your chain. The Brionson boundary is pi over a, where a would be the separation of the atoms in an atomic chain. Now, if this band is only partially filled, so if your Fermi wave vector is somewhere here, then this downward bending or the lowering of the electron energy, so the Brionson boundary does not affect it. But you can lower the energy of the system by moving your Brionson boundary to the Fermi wave vector kf, and then if that's the case, if your new Brionson boundary is here, you lower the energy of the occupied electrons, and therefore lower the energy of the entire electron system. The question is, how do you move the Brionson boundary from pi over a to pi over 2a, for example? That you do by distorting your atomic chain and induce a new periodicity of 2 times the lattice constant. So then in real space you would have a new periodicity, say lambda, and this lambda is directly related to the Fermi wave vector by pi over kf. And because of the distortion of the lattice, you get a modulation of your charge distribution. That's why piles distortion in one dimension is also equivalent to a charge density wave you sometimes observe in two-dimensional materials. So the question is, do we observe such a charge density wave or piles distortion in these grain boundaries? First, we can measure the Fermi wave vector kf in our sample. So this is the band gap state. It's very simple. Then from that we find the periodicity we would expect in real space. That's around 1 nanometer in this case. So meaning that our lattice constant should distort to around 3 times the lattice constant in this particular case. Now, let's see if we get that. So at room temperature, we see just the atomic corrugation as you would expect for molyselenide of 0.3 nanometer. But if we cool it down, indeed, you see a much longer periodicity, which you can compare here directly. This is room temperature, and this is the long corrugation, suggesting the formation of a piles distortion. If you do a line scan, you can still see the individual atomic positions. Here these little peaks, but the overall periodicity is 3 times the periodicity. So it really seems like these one-dimensional grain boundaries undergo piles instability, which is also known as the metal insulator transition, because you open a band gap, and that's the case of the piles instability, and makes the metal insulating, as you would expect for a one-dimensional atomic chain. Okay, I really don't have a clock in here, so I don't know how much time I have.
That's one.
After this one. Anyway, you just stop me when you get bored.
We
So-
never get bored.
Never get bored? Okay,
How
then,
long
I
do you think?
keep talking. Okay, so far I showed you these boundaries, and they have some interesting properties. We also showed that they may exhibit Tomonaga-Lattinger liquid, but I thought maybe that's not that interesting in the chemistry department. But what may be interesting is how these grain boundaries form. Okay, these are twin boundaries, and of course one assumption would be that just nucleate twins, and then they grow together and form a grain boundary. Oftentimes we see just these triangular loops, which is a closed grain boundary, so you have a twin inside and a twin outside. And another thing I want to point out here is that so the gray balls are molybdenum, and these are selenium, the green balls. That the grain boundary has a different stoichiometry. It's molybdenum 1, selenium 1, while the other one is molybdenum diselenide. So there's excess molybdenum in the grain boundary. So that gave us a simple idea. So in a thought experiment, you can take your lattice and just translate the part of the molybdenum sublattice by a fractional unit cell vector. And if you do that, then you would form a twin boundary on this side, a twin boundary on that. Inside you form a twin, and then on this side you are left with missing molybdenum that you would need to fill in, and then you form a closed transition metal, closed mirror twin grain boundary, which is triangular and is similar to what we see in STM. So the question then is, can we form these twin grain boundary loops just by incorporating excess molybdenum into the lattice? And is that the way why we get these dense networks if we grow with molecular beam epitaxy, that we just provide too much molybdenum? Right. So to test that, that's very easy to do. You start with a single crystal moly ditelluride in this case, which has no grain boundaries to start with, and then you vapor deposit molybdenum from an evaporator in ultra-high vacuum on the surface, and provide some kinetic energy by some temperature, and see what happens. So we just deposit molybdenum, and really start forming these triangular loops due to the incorporation of excess molybdenum, and you can, for molytelluride, you can add more molybdenum and more molybdenum, and you cover the entire surface with these twin grain boundaries. You can get up to 20% of excess molybdenum in the monolayer in molytelluride in this way, just by vapor depositing molybdenum on a single crystal surface. So this was molytelluride that I just showed. You can zoom in and show that these are these twin grain boundaries. We can do the same on molyselenide. Now on molyselenide, it has different kinetics. We form larger grain boundaries, but it also saturates and then eventually form molybdenum clusters that nucleate just in these edges, corners of the triangles, and then don't get more molybdenum, which is probably partially kinetically limited. While on molysulfide, we don't get any formation of twin grain boundaries, but it nucleates clusters right away on the surface. The molecule does not go in. Now, to understand that better, we asked Arkady and Tanu to do some Dft calculations to see what the energetic is. And so they considered excess molybdenum on the surface, and they considered 3 different configurations. One is just the add atom on the surface. The other one is put a molybdenum, extra molybdenum at the side of a molybdenum, so you form what they call a split interstitial site, where you have 2 molybdenum atoms in the side of a molybdenum, or interstitial molybdenum, which is in the center of the hexagon, just within the plane of the molybdenum. Now, for molytelluride, it's very clearly preferred to form an interstitial, while for single molybdenum atom, actually the split interstitial is favored in molyselenide and molysulfide, and the add atom is not favored at all. It's big. So if you put molybdenum on top, it really wants to go inside the layer. Now, if you add a second molybdenum atom, what happens is that both molytelluride and molyselenide like to form these interstitial sites and 2 molybdenum atoms next to each other. And for molysulfide, the dimer becomes favored, so it does not go in the layer anymore, and it's kind of the starting point of the nucleation of a cluster. So that seems to be in agreement with the experiments that shows that on molysulfide you do not form these twin grain boundaries, but you form clusters on the surface, while for molytelluride and molyselenide you can form twin grain boundaries, whereas these 2 interstitials may be the first step of the nucleation and growth of these grain boundary loops. So they took it a little further and started by adding 1 molybdenum atom at a time to molytelluride. So we had the first molybdenum likes to be in the interstitial side. You add the second molybdenum, goes also into interstitial side neighboring it, and pushes 1 molybdenum atom out into the next side. So then you have this cluster of interstitial molybdenum. You add the third molybdenum, which goes here, and then it pushes those molybdenum atoms over, and then you already start seeing the nucleation of a twin grain boundary, adding a 4th molybdenum atoms and make it grow. And as you can look at that for 5th molybdenum atom, you can see that the growth of these twin grain boundaries just proceeds. It gets larger and larger, and importantly, it's all energetically downhill. So they like to add more and more molybdenum to these twin grain boundaries to form larger loops. So that seems to make a lot of sense, and together with our experiments, that this is the mechanism for growing twin grain boundary loops. So it's not the merging of grains that form a grain boundary, but it's incorporation of excess molybdenum into the lattice that forms these molybdenum-rich grain boundary loops. All right. Now, why is that interesting? We asked Stefano in Padova to do some electrocatalysis on it, so to look at hydrogen evolution reactions, and Arkady then did some Dft calculation. And essentially what we saw is an enhancement of the hydrogen evolution, which makes sense with the Dft calculation for the barrier of the hydrogen evolution. If you see, just if you have perfect molytelluride, then you can have the hydrogen either diffusing over the top or the top of molybdenum, but in either case you have a large barrier for hydrogen evolution. But if you have twin grain boundaries and you go next to it, the hydrogen likes to go into interstitial, and that lowers the barrier for hydrogen evolution. significantly. So by introducing these twin grain boundary loops, you can increase the activity of moldy telluride, for example, where we have to say that tellurides are not really probably practical electrocatalysts, but it's just demonstrations that these grain boundaries can enhance activity.
Did you send them samples, or did you? Was he making it in his lab, or did you send them samples, or how?
We sent samples.
So you can mail that through here. That's
Yes.
it doesn't do anything. But that is anyway on air or something, or on
So this is an electrolyte solution.
liquid.
Yeah, so I guess you can clean somewhat with the electrochemical cell. But they are fairly stable. The molybdenum selenide in particular is very stable. We took samples to the synchrotron in Paris. We took samples, we specifically built a vacuum suitcase, which cost us thousands of dollars to ship it to Paris. And we took the sample in air, and there was no difference. So they survived exposed into air very, very well, to molyselenide.
But you get a carbon layer on it or something.
You can heat it up in vacuum and clean it fairly well. So we didn't see much contamination on molyselenide.
So then you can send me a sample.
Yes.
How do they look like? That's what's.
Okay, they're different kinds. So the problem is, if you have a single crystal, molytelluride is probably less stable, and molytelluride you can buy them commercially, and you get different flake sizes. Sometimes you get 5 by 5 millimeters, that's larger, and sometimes you get little flakes. Molyselenide is a little larger, but I guess what we've done is for the MBE grown one on a molysulfide substrate, or you can grow it on graphite. You can have a large graphite sample, 5 by 5 millimeter graphite sample, and grow molyselenide on that and test grain boundaries. The disadvantage is that in experiments you probably would like to compare with or without grain boundaries, and we haven't been able to grow molyselenide without grain boundaries. So that's also nice. It would be nice for the electrocatalysis. But if you have a single crystal, and you have a single crystal without grain boundaries, you can reduce the grain boundaries and compare. Anyway, I guess we can talk about it. Yeah, so that's for that. Another one is metallic contacts. Well, if you have molytelluride, you want to use it, let's say, for semiconductors. The simplest problem for semiconductor industry is to make a metal contact with a semiconductor, which gives rise to the Schottky barrier in the ideal case, which is if you have a semiconductor, your Fermi level, depending on the doping, but if you make a contact, then the contact potential depends on the work function difference, and you shift your Fermi level freely, depending on the work function difference between your semiconductor and the metal, that gives different contact potentials. However, if you deposit your metal, and your metal forms defects, then you get defect states, as we shown within the band gap, and those defect states then will pin the Fermi level at the neutrality level of the defect, and then the position of the valence band maximum to the Fermi level becomes defined, as defined by the defect state in the material. This may be an issue for 2D materials, especially for molytelluride. We think that if you deposit metal, we get this grain boundaries. There has been a recent Nature paper that looked into that, compared metal deposited by vapor deposition and metal deposited by transfer method. So they have a solid metal and transferred it. Only if you have the solid metal transferred, you have a nice Schottky behavior where the electron barrier scales with the work function of the metals. While if you deposit metals, then your electron barrier essentially becomes independent of the work function due to the pinning of the Fermi level of the defect states. Now, in this case, it may be very different, but for molybdenite, we certainly expect that if we deposit metals on molybdenite, the metals go into the layer, forming defect slits. And to show that is more universally true than just for depositing molybdenum, the Dft calculations for a set of transition metals, and which also this reddish line here is the interstitial, and for most of the transition metals, the interstitial configuration is energetically favored over add atoms or split interstitials. So for all these transition metals, you would expect them to diffuse into the layer of molybdenite, forming defect states in the molybdenite and such, crossing the opinion of the Fermi level. We can take this, of course, a step further and ask, well, if we can modify the molybdenite with these metals, can we induce some interesting functionalities, maybe in the molybdenite? This department may be asking if we can induce some interesting chemical properties. The question we ask, can we induce magnetism? And so we looked at the magnetic moment, or the theorists looked at the magnetic moment if you put vanadium or titanium in it. Vanadium has a magnetic moment of 1 Bohr magnetron, while titanium is non-magnetic. And so we tried to figure out if there's really magnetism. So again, we started with molybdenite single crystal. There's some native defects, which may be molybdenum antisites, as some people suggest, but overall it's fairly defect-free. There's some weak ferromagnetic response if you do magnetization versus magnetic field measurements, just a hysteresis measurement, but it's really very weak. We can take that crystal and just anneal it in vacuum to 600 Kelvin, and what we start forming is what we think are tellurium vacancies, which show up nicely in SDM images and kind of correspond to simulated SDM images. So at 600 Kelvin, we just dissolve some tellurium from the surface. But the magnetic signal doesn't really change. So